and then go on with more relative motion. As relative motion continue. Any logistics questions about the course or other general questions before we go on with this?
Did our ranking as the most difficult course change?
Blah, 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 blah.
Did our ranking as the seventh most difficult course change?
This was never seventh. This was harder than seventh. So we were implicitly sixth or less. Was the exam, should it got harder or easier at that exam? Okay. So we have this turntable on this truck that's moving, and on the one hand, we want to know what this bug is doing here. On the other hand, the information we're given about the bug is information about how it's moving on the turntable. It's moving on this straight line on this turntable with some r, that's some function of time. And given that information, we want to try and figure out the absolute velocity, or the velocity relative to the fixed reference frame. We're talking about the velocity of some particle relative to the fixed reference frame. And what we say that is the velocity of the origin of our moving coordinate system plus the velocity of this bug, I'll call it P or B or bug, whatever we're going to talk about it, relative to the moving coordinate system, plus the fact that if the moving coordinate system is rotating, even if it's not translating, and even if the bug is dead and squished on the turntable, that it's still going in circles, and we have this omega crossed with the position of the bug relative to the center. And it doesn't even have to be a center, but relative to the reference point we're using on that moving coordinate system. And the fancy language people use for this omega is we should put the omega of this body relative to the fixed frame. But since there's only one body, and implicitly we're always doing things relative to the fixed frame, you don't always bother with all those subscripts. Any questions about this formula? How to plug in this formula in this problem? Okay, now next we'd like to know the acceleration of this bug relative to the fixed reference frame. And I'll just call this the acceleration because we're only looking at one particle. And obviously we're talking about, we care about the acceleration in mechanics, so it's relative to the fixed frame. And what is that? That's the sum of terms like this, all of which are intuitive, plus one extra term. So we can just remember what those terms are. And why don't I give you a minute, without looking at your notes, to try to fill in what goes on over here. Just don't look at your notes, and you have like 2 minutes. Try to fill in what's over there while I erase the board over here. Just see how good a job you can do of it, and then I'll tell you how it goes, and you'll, in the process of thinking it through, maybe you'll learn it better. Just make your best attempt. Try and do it yourself. Don't do it with your friends. Struggle. Just try to do it. Have you done it? Come on, try. You got to have some guesses there. I have to admit that this class before ours looks harder than ours, right? So if ours is 6, theirs is 5. Okay, are there any questions about this before I'll still tell you the answer here, but any questions about how to think about this before I fill it in? Yes?
Well, before the truck example, we had just an
Yes.
Rotating?
Yes.
Can we treat this as the same thing? It's just you have the turntable in the truck because the truck rotating while accelerating would be ridiculous.
Yes. The truck translating and the turntable rotating on top is just a way of showing you how this turntable is translating. I could have erased the truck altogether and just look at the turntable. The truck is just to help you see how it goes. So really all you have to focus on is the fixed frame and the turntable. Ignore the truck. Any other questions? Yes?
I don't know if you want to answer it or not. Like the B and the A, right? So you take the derivative of B to get A.
That is not correct.
No?
Okay, that is completely correct.
So I can do it, and I get everything you get except for that 2.
Right, so the question, if you know position as a function of time, we differentiate that to get velocity as a function of time. That's correct. If you know velocity as a function of time, we can differentiate that to get acceleration at any instant in time or as a function of time. The trick here is without giving those functions of time explicitly, but just being given the instantaneous positions, velocities, and accelerations, can we get, and the relative accelerations, can we get that result? And that, if you want to do that, the differentiation is subtle. And if you want to know how to do that differentiation, you read the book or you come talk to me in office hours. So how you do the differentiation is a subtle business. Yes?
I was talking about the general formula, not for a specific time. Just the general formula. For any V, you have that.
Right, that's what I'm talking about too. I'm saying that the differentiation, if you have position as a function of time, or let's say velocity as a function of time, you just differentiate. The question is, how do you think of that formula as a function of time in order to differentiate it? And that differentiation has some subtlety to it, which you can't just see by doing the product rule there. Okay? Okay, so how does this work? Here is a miracle that we are blessed with more than we deserve, which is that if you have a bunch of different effects, the result of those effects is the sum of the effects separately. And there's no reason to think, without knowing the details, that it should work out like that so much in life, or in this problem, but it does. So, in order to get this answer, what we can do is think of all kinds of different situations where all we have is one term, and then what we get when we have all the terms together is we just add the results. And that's how this problem works out. It's quite different from this thing that I've been preoccupied with the past week or so, which is this bicycle dynamics problem. Let me just tell you about the bicycle dynamics problem, just as an analogy, to show you how that's different here, is bicycles can balance themselves. Amazing fact. Bicycles can balance themselves. And why do they do that? And, well, we have the differential equations, and those differential equations are of the general type you're learning in this class, but they're three-dimensional and they're complicated. We can write them, they're fourth-order differential equations. They're two coupled second-order differential equations. We write these nonlinear versions, and there's 25 parameters in there. The height of this, and the length of this, and the angle of this, and so on. And then people say, why does the equations work out that the exponential solutions are decaying rather than growing? And there is no simple answer, I believe. Is there a gyroscopic effect? Yes. Is there effect from the distance that the steering axis is from where the wheel touches the ground? Yes. Is there an effect from the angle of the head tomb? Yes. Is there an effect from the center of mass position? Yes. And can these all affect stability? Yes. So if you have this, it's good. If you have this, it's good. If you have this, it's good. And you add them up, it's good? No. So that particular problem works out that there are all these different effects, but you can't just say they add. They're all just all confounded in a complicated way. And you can't understand the stability of a bicycle by saying there's this stabilizing term and we add this stabilizing term, and if we have both of them, it's even more stable. It's just not true as far as we understand. Okay, it's just complicated. The variables are all complicated. This problem right here is simple in the way that we have different effects and we can add them up and it turns out we get the right answer. Okay? So, How can we do this to understand it in a simple way? Well, let's assume the bug is dead and the turntable is not rotating. What's the acceleration of the bug?
The acceleration of the truck.
It's the acceleration of the truck. So that's the first term, it's the acceleration of the truck. That's O prime relative to O. And that was a rhetorical question. You did not need to answer it out loud. But that's okay, now let's take another special situation. What would happen if the truck engine was dead, the turntable motor is broken, but the bug is crawling away on this line? That's just your old problem. That's a particle moving on a straight line. Nothing but that. And that is what we would call the acceleration of the bug relative to the moving frame, which would be the same as the fixed frame in this case. If we wanted to fill this term in, this term would be, say, x double dot I. If we wanted to fill this term in, it would be r double dot E sub r, where E sub r is a unit vector in the direction of the line. Now that's going to change with time, but at this instant in time, if we know the orientation of this line, then we can write what that term is. So is that much clearer? Okay, now let's do another simple situation. The bug is dead again. The truck engine is dead, but the turntable motor is working. Going round and round. Bug don't. So what's happening is we have a bug going in a circle. And if it's going in a circle at constant rates, then we have an acceleration which is minus omega squared, the position of the bug, relative to the center of the circle. Okay. And how could we write that? This particular term we could fill in as r E sub r for the instantaneous. What if the turntable is not just going around and around, but maybe it's not even going around at all? But you just turned on the motor to the turntable, so just when you turn on the motor to the turntable, it starts to accelerate. So the bug is going to have an acceleration along the circle it's going on. The truck's not moving, remember? The bug's not crawling, remember? The bug's just going to go in circles. It's going to start accelerating in the tangent direction along the circle. How much is it accelerating? It's how much its speed is increasing. What's the speed? It's theta dot r. How much is the speed increasing? It's theta double dot times r. Sorry, in the tangent direction. How do you get that direction right? Is you write omega dot k cross this position, which is the position of the bug relative to O prime. And that thing, again, is the same as that thing. Is that much clearer? Okay. Now, that's as far as you can go with your easy intuition. So all these effects add, plus one more effect, which is intuitively not so obvious, but I will try and show it to you a little bit, the intuition of it, which is this one extra term, which is omega, or omega k, crossed with the velocity of the bug relative to the moving frame. Now, if we want to understand this term, we have to try to find a situation where that term occurs and all the other terms don't occur. Yes?
In the previous class, you said that it was 2 omegas.
Yes. So in this class, I was half right. Okay, so now can we find a situation where that term is there and all the others are not? Well, if the first term's not there, the truck is not moving, or at least it's got constant speed, but let's make it simple and say it's not moving. If this term's not there, either the bug is not moving or it's moving at constant speed in a straight line in the moving reference frame. If we want this term and not this one, we have to have the bug going at a constant velocity along this line. So it's constant velocity along this line. Of course, it's moving in a crazy path, right? The actual path of this bug, while this trug is moving, is some crazy spiral thing. But if we want to kill this term, we're going to say constant velocity in the moving frame, which means the bug walking at a constant rate along the line. We want to kill this term. How can we kill that term? Well, we could make the turntable not turn, but then we're going to kill this term too, and we want to keep this one. So how do we keep this one and kill this one? Is the bug has to be at the origin. So we have to look at the situation where the bug is passing through O prime. How do we kill this term? Well, the bug is passing through O prime, or we can say omega dot is 0. It doesn't matter whether omega dot is 0 or not, but let's just make it 0 so we don't have to worry about it. Okay, so special case. We're going to have x double dot equals 0. We're going to have r double dot equal to 0. We're going to have r itself equal to 0. And that gets rid of these terms. Let's take omega dot.
Why does it make it simpler?
So when we're thinking about this problem, we have less to think about. It doesn't make the equation simpler, it just makes it simpler to think about. Okay, so now how are we going to think about this problem? What we have is we have this point O, which is O prime, which is going to be still. And then we have the bug walking along this line, which is passing through O prime. So here we have our O prime, and we have the bug passing through this line. Now, this is the line at t. Now let's look at this line at t plus delta t. And just for simplicity, let's just look at the velocity of the bug when it's right here. So here's the bug at t. And here is the bug at t plus delta t. And this is the velocity of the bug at t. And this is not the velocity of the bug at t plus delta t. This is the radial part of the velocity at t plus delta t. And we have to add to that this delta r times omega. And this is the velocity at t plus delta t. Okay, so this bug is crawling along this line, but the line is rotating, and we're going to look at it just as it passes through the middle of the turntable. And in that situation, if we take the truck is not moving, the angular velocity is constant, the bug is moving at constant speed, we want to look at how does the velocity change with time, because how the velocity changes with time is the acceleration. And what you see is even though the bug's moving at constant velocity in the rotating reference frame, its velocity is changing. In fact, if you look at the path of the bug as it travels here, its path is some crazy path like this. So it comes in like this, goes out like this, and right in this situation is coming in tangent to this line here, and then it curves around like this. So this is the path of the bug as it's walking on this line, which is turning around. Okay, now we're trying to figure out how big it is, and what we see is there are two reasons the velocity changes. One is because the direction of the line is on changes. So So its velocity changes from this to this. And the other is when it moved from here to here, it suddenly picked up a tangential velocity because it's now got this circular part of the motion, which it didn't have here. Both of these things are proportional to the velocity itself, the change from this one to this one, or the change to here, because the faster the velocity, the farther it moves out of the circle in a given amount of time. So this is the 2 omega v term. There's a change in velocity proportional to the velocity, because it's changing directions, and there's this change in the circumferential part, and those two add up, which give us the 2 here. Okay, so that's the intuition about that term. I'm not claiming that you should be able to derive that term accurately and correctly and have that intuition at the beginning to write down all 5 terms there, but that last confusing term, at least this gives you a way to think about what it is. Yes, your question, please.
Can you say that again?
That, for English. When you say this, or that, or it, people have trouble knowing what you're referring to.
This one, the 2 vectors, the 2 terms. I couldn't quite comprehend that. I'm a little slow.
We're trying to understand this term here.
Right.
We're trying to understand it by looking at a situation where all these other terms are 0. The situation is a bug passing through the middle of the turntable while the turntable turns. The question is, what do we mean by acceleration? We mean change in velocity per unit time. That's what acceleration is. So let's look at a small amount of time and look how the velocity changes. Here's the bug with some velocity as it passes through the origin. A little bit while later, it's traveling on a line like this, and its velocity is the velocity along the line plus the velocity along the circle it's going around, because it's now going in circles around a small radius circle. What's the difference between this velocity and that velocity? Is there are 2 terms. One is this arrow is different from this arrow, and the other is that this arrow is different from this arrow. Both of those are proportional to the size of the velocity, and both of them are proportional to the rate of angular acceleration, angular velocity.
Which arrow is the velocity slightly after?
This is the net velocity after delta t, which is along the new line plus a term which is related to the velocity at this later time has a circumferential component.
What's the tangent one? I understand the radial one, but what's the
What's with the tangent one is that when it's out here, it's on this. Here's this thing, the bug, crawling on this line. It's going to pass through this middle point. Here's the middle point. Now it's going to be here. This thing is going to advance to here. Now, what's its velocity when it's at this point? One thing is it's moving radially, and the other thing is this thing is turning. And it's got a velocity due to both of those effects.
Yeah.
One is it's going radially in a new direction, and another thing is it's turning. The change from here to here is the change in this direction plus this radial term. And both of those are products of omega and v, and that's where the factor of 2 comes from. Yes?
So the only time when you can see the 2 omega r effect is when it's coming right out of the center. You can't, once it's out of the center, you get this centripetal acceleration also, right?
Yeah, the only time that I know of that you can see this effect in isolation is when you kill all these other terms. And how do you kill all these other terms? You've got to see one at a time you're stuck being in the middle there. Now when you're not in the middle, that term is still there. It's just harder to understand it. Does that address your question? Okay. So here's this formula, this 5-term acceleration formula, which I hope was as good for you as it was for me. Now, what do you do with this formula? Is you can now use it to try to figure out things about the velocities and accelerations. Use it, either that one or this one, to figure out things about the velocity and acceleration of parts that are moving funny ways. So for example, if we look at the slider crank, did in your lab, let's lay it out in a horizontal orientation. We have this mechanism that looks like so. And we have this R, and we have this L, and this is going to go around with some theta. And we'd like, for example, to know how this X changes in time. And there are various ways to try to figure this out. But one way we can try to figure out what's going on is by using these formulas. I'm not going to do this problem in complete detail. Okay, let's call this angle here phi. Before we're going to get anywhere in figuring out velocities and accelerations, we've got to figure out something about positions. So can we even find, if I'm given, let's say we're given R, and we're given L, and we're given theta as a function of time, and we're trying to find, say, phi as a function of time, or we're trying to find X as a function of time. But really, we don't care about these things in detail. We only want to know at one instant in time, so we can do our mechanics at one instant, then we can do it at a whole sequence of instants. But we really want to say is given R, L, and theta dot, and theta double dot, we want to find, say, phi dot, phi double dot, X, X dot, and X double dot. We don't need to find all the whole function. The idea is to somehow not have to differentiate functions of time, but use the instantaneous values, which is what this formula is all about. It's a way of avoiding doing a long differentiation of position as a function of time and just using something about instantaneous values. So somehow this encodes the product rule and the chain rule and things like that. Okay, so the first thing we've got to do is figure out things about the configuration. So the first thing is just a 10th grade geometry problem. So if I gave you theta, R, and L, can you find phi or X? Or we call this angle alpha. So how could you do that? Well, there are lots of ways to do it. Anybody give me a suggestion? Anybody who has not asked 3 questions yet today? Or even 2? The law of sines, and how are you going to use the law of sines? So we can figure, if we can figure out theta and alpha, then we can find phi, because these all add up to pi, 180 degrees. So let's just try and find alpha instead of phi. You could use the law of sines. How do you find, what is the law of sines about? One way of thinking about the law of sines is about saying this height is equal to this height. Or you can say sine of theta over L equals sine of alpha over R. But both, that's equivalent to saying, using the Lorentz and so on, let x equals x, and think about this height equals this height. We have 2 ways to think about it. One is in terms of this triangle, one is in terms of this triangle, set them equal to each other. So what we can say then is that sine of theta over L is equal to sine of alpha over R. If you multiply this by R, multiply this by L, this is like saying H is equal to H, Lorentz. Okay, so given this, we can find alpha, and given this, we can find phi. Right, because phi is equal to pi minus alpha minus theta. Okay, so now we can find the configuration. Now, given this configuration, can we figure out things like what is x dot and so on? And what we can do is we can take this point C here, and then we can use the Laurie-Anderson song again. So what we can say is that the velocity of C is equal to, go ahead, write it in your notes. Everybody can follow that equation, right? Okay, so what we do with this is just like this thing where we say h equals h, and think about it two different ways. We've got the velocity of c equals the velocity of c, and we can think about it two different ways. What are two different ways we can think about the velocity of c? On the one hand, c is stuck moving on this line here. So we have an I, and we have a j. So we have a simple way of thinking about that, which is that it's x dot I. Now we have a different way of thinking about the velocity of c, is we forget about the ground here, and we say we've got theta, and this thing is spinning around. We can make this a moving reference frame. So we could think of this as being some body which is moving around. And we can then think of this as a point which is moving relative to that reference frame. Actually, it's not, it's still. And then we can try to think of the velocity of c as moving relative to this whole, this thing moving relative to that thing. So we can put it together that way. Actually, there are a couple ways to think about that. But I'm going to do the one where we think about this as a moving body. If this is a moving body, what is the angular velocity of that moving body? Well, it's rotating at some rate, which is theta dot plus v dot. So it's theta dot plus v dot times k. Okay, so now we're going to plug in this formula. The velocity of c is going to be, we'll call this thing O prime, is going to be the velocity of O prime plus omega, and this is going to be omega of that body, crossed with the position of c with respect to O prime, plus the velocity of c with respect to that moving body. Now we need to fill in these terms. This is the general formula. We need to fill in these terms. Let's start with, in this example, what is this term here? Or for those of you who weren't paying attention until you heard the word what, what? In which case you answer, when in doubt, 0. So this term is 0. By the SAT reasoning that when a professor asks a question in class, the answer is most often 0. Which is not what you're supposed to be learning here, but it's part of what you're learning. Anyway, why is that 0? Is because here's the dead bug on this moving body, and this point C is not moving relative to this body. Okay. Now, what are the other terms here? This term we can figure out by looking at some unit vector in this direction, which we can call E sub r. And we can also add a unit vector here. We can call this E sub theta. This has to do with the current configuration. And this term, we can write it with cross products, or we know this thing is just going in circles. So that term is r theta dot E sub theta. This term, we've already figured out, is theta dot plus v dot times k. And this term is what? Well, we know where this point C is. We know where this point O prime is. We have to write a messy formula for this term, which we could set out writing by solving for these angles and so on. So we have to figure out where this point is using that geometry of the instantaneous configuration. But we know what this thing is. It's a messy thing, but we know what it is. When we write this whole equation down, we're told what theta dot is. We're told what theta is, so we know what this is. So we can solve for x dot. Okay, so when we take this equation, it will tell us what is x dot. Dot of the dot. What else will it tell us? If we dot it with j, it will tell us what is beta. So it's algebra mess, which I'm skipping. Yes?
Is B of C respect to B 0 because C is part of the body?
That is correct. It's as if there's a dead bug at the middle of that hinge connected to the cylinder and that piston. Yes? Are you happy? Yeah. Okay. Now, what if we want to figure out the acceleration? So we can say the acceleration of C is equal to the acceleration of C. On the one hand, we know that that's x double dot I. And on the other hand, we know it's this 5-term acceleration formula, which has in it the accelerations of O prime with respect to O, plus the acceleration of C with respect to this moving body, two intuitive terms, plus this negative omega squared times the position of C with respect to O prime, plus omega dot, which is going to be, I'll just leave it like this, omega dot k cross the position of C with respect to O prime. 1, 2, 3, 4 terms, and then we need plus 2 omega k crossed with the velocity of this thing with respect to the moving frame. Okay, this term we know is 0, so we don't have to deal with this Coriolis term. At least in this way of thinking about the problem, you don't have to worry about the Coriolis term. This term, we know what it is. That is r theta double dot e theta, because it's going in circles faster and faster, plus a centripetal term, which is minus theta dot squared r e sub r. Well, how about this term? What is that? Or in other words, 0. Why is that? Because point C is stuck on that body. That term is 0. What about this term? Here is the mess, but you can figure out what that mess is. So it's known in terms of the given configuration. It's a known mess. How about this term? Well, there's our theta double dot plus phi double dot. So there's one of our unknowns. And then we have this known mess over here, and this is already 0. So what we have is two unknown scalars in this equation, x double dot and phi double dot. If we dot with I and dot with j, we get two scalar equations. So we can solve for this. We dot with I and dot with j. It will tell us then x double dot and phi double dot. It's a mess, but it's all doable. What's the good of that? Now we could do mechanics if we wanted to. Or now we could solve for the acceleration of part of the engine in terms of the other parts of the engine. Okay, any questions about this example? Okay, so let me try a different example. And this is going to be that centrifugal gun again. example, but I just want to do it with this new apparatus. So we'll take this stick, which is spinning around in circles. There's a motor here. And we've got this bead on this stick. And it's out here some distance r. And this thing is some theta, which I'm going to say is theta times t. So I'll say omega is equal to a constant. For the purposes of this calculation, I'll say that this point is O, and it's also O prime. And I'll call this my moving body. So when we draw a free body diagram of this bead, it's just like when I did it last time. The free body diagram has some force here. No force along the rod because we assume it's frictionless. So even though this thing is going to go flying out, which we did, we watched it flying out, there's no radial force. Why does it fly out if there's no radial force? That's something for you to think about when you go to bed tonight. Just for fun. It's effective, even though there's no radial force.
Have you ever seen a student with that?
Not on purpose. You want to try? Who said that?
No.
So if we're going to figure out how this thing works, we say that the sum of forces, external forces, is equal to the mass times deceleration. What do we have for external forces? If we pick unit vector here in the ER direction, and another unit vector here in the E theta direction, for forces we have this n E theta. Now, instead of using polar coordinates, let's just use our new formula. So our new formula says we have the acceleration of O prime relative to O, plus the acceleration of this particle relative to the moving frame, plus a minus omega squared, the position of the particle relative to O prime, plus an omega dot crossed with the position of the particle with respect to O prime, plus 2 omega cross the velocity of the particle with respect to the moving frame. We want to plug in this formula and see if things work out well for us. Okay, why don't you try it yourself for a minute, and then I'll do it. Wait, did you do it already? You've done all the terms? You believe that you could do all the terms? That can do, don't want to, work doesn't work in exams. You're not allowed to do it here.
Doesn't radial velocity result from the fact, or the radial velocity results from the fact that you have the tangential velocity, but because the path that it can travel is changing, but you don't choose that velocity, eventually it adds up to that moving along the path.
Exactly. No, I actually believe I followed what you said, and I probably would have said almost the same thing. So let me draw a picture. This is before we do the technicalities here. We have this rod here, we have the speed. What is the path of this thing as it flies out? It's something like this, some spiraling out. At any instant in time, let's catch it right here, the force on this thing is in this direction. And although there's no force for the radial component, the force does have a component along the path. At that instant in time, that force component is orthogonal to the radial direction, but in terms of the path, it's got a part along the path. And this direction, by the time you get over to here, is along the path. Or largely along the path. So all you need to do to make something go faster and faster is to have a force which has a component, some component along the velocity, and this has that. Okay. So let's work on this term. Blah blah blah. Zero. Why says 0? Because we picked our O and O prime to be coincident. They're not moving one relative to the other. What's the acceleration of the particle relative to the body? That's r double dot e sub r. It's just going in a straight line relative to the body. The direction of that straight line is changing in time, but at any instant in time, it's just r double dot er. What's this term here? That's minus theta dot squared times r er. What's this term here? Zero, because we said that the angular velocity was constant. We just made that assumption. And what's this term here? This is something we have to worry about. This is 2 theta dot k crossed with r dot e sub r. So we want to put these together. We get m e sub theta is equal to, we have a 0 here, we have r double dot e sub r. Actually, we have an r double dot minus theta dot squared e sub r. And then we have plus this term, here's k crossed with e sub r, which is e sub theta, so plus 2 theta dot r dot e sub theta. And this is exactly the equation we had when we did this with polar coordinates. When we wanted to see how this thing moves, ironically, we figure it out by getting rid of the force which causes it to move. We use that force implicitly by setting up the problem, but by taking the dot product of both sides with e sub r, the force drops out and you get a differential equation for the motion. Any questions about that? Class today was too fast, too slow, too boring. Why was it boring? Too interesting? I apologize for making